sort of between LLMs and recommender systems. So a quick sort of rundown of our agenda for the day. We're going to be starting with the typical how to go about and read research papers, then go into this specific paper, the problem and the proposed solution within the paper, then quickly cover the recommender system space as it is up until I would say 2023. I'm still catching up with sort of like the 2024 space. The approach that this paper has taken towards like merging together LLMs and recommender systems, the results that the paper has shown, and then we'll go about a quick discussion, maybe take a few questions from the audience as well. Um, so yeah, going over a quick intro of how to read papers. Typically, I like this phased approach. I came across it in like an NVIDIA article. It got like pretty popular in like research circles. So most people like this phased approach of reading papers where you don't necessarily have to sit down and try and digest the paper in one shot. Rather, first start by reading through the introduction section, abstract, and conclusion to sort of figure out what this paper is about, what this paper could sort of contribute to your knowledge. If it seems interesting, then go ahead and read the paper. If it doesn't seem like it's something that's interesting or applicable, you can definitely drop the paper then and there. I know a lot of people feel regret about if they start a paper, I have to finish it. And until I finish it, I can't pick up another paper. You don't need to have that guilt. If it doesn't feel good, drop it then and there. Then you have to go about reading the related work or sort of like the prior research sections in the paper. This is to sort of develop a mental map of the research in that space, like what are the typical metrics, what are the benchmark models that uh, in the space, and how exactly this space came to be where it is right now. So a mental map sort of helps you place this paper and sort of figure out the value of this paper. So we'll go over the mental map for recommended systems in a bit, and hopefully that will clear things up. The next is sort of trying to understand, not to analyze, but understand what the approach of the paper and what the results are. So you typically go over the methodology and the results section. You're just trying to understand what metrics did they use, what benchmarks did they use, what is the architecture of the model, or what is essentially the proposed solution, and why they made all these design decisions. Try and ask as many questions as you can here. The idea is to understand as deeply as possible and maybe not to start questioning it, but just to understand why they're doing what they're doing and ask as many questions to improve your understanding as much as possible. Then comes the analysis portion of the paper, where you again maybe take all the mental map notes you made from your research space. You take all the approach and understanding that you have developed and try and figure out if there is any fault within the paper, or try and figure out, okay, they made this design decision, but did they actually explain why they're making this choice? Could it have been done another way? A few things like that to sort of A, better understand the space, and B, sort of question the paper, because at times we have seen certain research get very popular, but maybe like a year, 2 years later, people come and start questioning the work, and we sort of figure out that, okay, maybe it wasn't as seminal as it was when it was released. And yeah, in the last phase, sort of like the best way to learn is discussing with peers. You always don't know everything that you may need to know when you're new to a research space. Like definitely in LLMs and recommendations, I don't know everything I need to know. So it's always good to talk to other people, get their perspectives, and it sort of helps you get exposed to questions that you might not have asked yourself. So yeah, discussing with peers, the research hangout was sort of built for this. So definitely, if you have any questions, feel free to drop them in the chat, or when it comes to discussion section, feel free to call them out. Now, coming to the problem and solution of the current paper, the HLLM paper. So the paper is trying to bring together two fairly popular domains, which is like the LLMs domains of question answering, which has dominated like primarily question answering, and recommender systems domain, which is pretty industry relevant area. The idea being you want to try and predict what the user will like next, or user will like to buy next, or interact with next. So those two problem areas, how can we combine? The three main questions that they're trying to answer through this paper is the is there value of the LLM's pre-trained weight? Essentially, what most researchers call as world knowledge. The fact that LLMs have a huge amount of parameters and they're able to condense everything, that all the text that they have trained on, to a certain world knowledge. Does that world knowledge have any value in the context of recommender systems or not? Second question, would fine tuning in the context of recommender systems be essential? As in, can we use the world knowledge as is, or do we need to fine tune these LLM models to be impactful in the recommender systems domain? And the last one, we've seen that with LLMs, as you increase the parameter size, as we go from 1 billion to 7 billion to, I guess, I know like 200 billion, um, the performance sort of increases. Do we see that same performance increase when it comes to using LLMs within recommender systems? And another sort of subsidiary of that performance, can it be actually practically used? Is it like efficient enough that it can be used for a recommender systems model, which is a fairly very demanding real-time model? So can it actually be used in those kind of practical settings? So these are the three questions that the paper is trying to answer, and they do say yes to all of this in the sense that LLM's world knowledge does help. It is required to fine tune the model to be sort of like good in the recommendation system space. We do see the economies of scale, sorry, not the economies of scale, the fact that as scale increases, performance also increases come into play here. And we do see that the at least others state that it is efficient enough because they do conduct an online test or an A/B test to showcase that these kind of models can be used in like real life recommender systems. So that's basically, like I said, the first phase. What is the value of the paper? What are they trying to address? And what do they say about what they're trying to address? Now, coming to the mental map, the second phase that I mentioned, trying to understand the recommender systems research space and the involvement of LLMs in that recommender systems research space. So in terms of mental map, the three sort of dominant methods that you need to keep in your head is content-based filtering, primarily using user attributes or item attributes to sort of figure out what the user will like next. A very simple system is a demographic-based system based upon where you log in from. The website is able to get like some geo info, make guesses about who you are, and based on that provide certain recommendations like Netflix based upon where you're logging in from, the for you, or the top movies that would be recommended change from geo to geo. Collaborative filtering systems, these are essentially if you like certain things, other users who like those things, whatever they like, you're likely to like. Essentially, it's sort of building on this concept of what people like, you will also like. So there are two sort of, actually three different ways of approaching collaborative filtering. Memory-based approaches, where what I mentioned exactly is applied, in the sense that whatever items you liked before, what are items similar to that, you may like those items. Or whatever users are similar to you in terms of what items you like and dislike. Whatever this user liked, you may also like. So there are two different ways of approaching memory base. Model base is a bit more, it extracts a bit more latent features. It gets a bit involved, but the idea is you create a matrix of user item interactions, and there is a different approaches, most common being matrix factorization. And the idea is you can extract out latent user features and latent item features, using which you can say what if given a particular user and a particular item, whether they will actually interact or not. Matrix factorization is the most common one that you just need to keep in mind. And the next sort of set of models is the deep learning models that we have seen, I would say, post 2015, 2016. WDNs, wide and deep neural networks that were popularized by Google, graph neural networks that are sort of becoming kind of popular nowadays because of the idea that it's not just what the user liked that matters. It's the sequence in which they got to the item that they like. They liked item A, B, C, D. That sequence actually matters, and that's what GNNs, graph neural networks, are trying to capture. Then comes two towers. This is probably one of the most popular architectures in recommender systems, essentially building one tower for a user, one tower for an item, getting the user embedding, getting the item embedding, and trying to combine both. So these are like some common methods in collaborative filtering. And hybrid methods is nothing but combining content and collaborative filtering. So it's good to keep in mind this sort of three buckets in your head. The approach that we're discussing today sort of falls within hybrid approaches, but recently, like I mentioned, people have started sort of putting forward this claim that it's not just what the user liked that matters, it's the sequence of their interaction also matters, that they liked item A, then B, then C, then D, and nowadays they're liking item E, F, G. That sequence, that temporal information actually does matter, and this sort of very recently, I would say like 2018 or 2019 onwards, yeah, late 2015 onwards, the sequential idea recommendation came into place. Two dominant models in that space is like 𝗏𝗏𝗺 and 𝗨𝗏𝗃. Both of them essentially they take your user interaction history, as in what items did the user interact with, and they apply attention on top of it to figure out what items in your history are gonna be most relevant to what you're gonna like next. So what they're intuition wise, what they're trying to capture is, are there any short-term interests that this model needs to pay attention to, and are there any long-term interests that they can get from the user interaction history that they need to pay attention to. So that's where sequential recommendations sort of come into place, and they have been pretty close to SOTA nowadays as well. Now, this is sort of the recommender system space. Coming into the LLM space and how LLMs have been used in RecSys thus far. Primarily, they've been used to create like embeddings, like items usually have a rich title, description, all those things. So creating embeddings and helping make the item embeddings a bit more informative. That's always been done with like normal like language models like BERT and everything. LLMs, because they have more world knowledge, they have been used to try and improve the quality of those embeddings. So this summarization of info is like a common place where you will see LLMs used within the RecSys space. And also they have been used to sort of change how recommendation systems work, in the sense that typically it's like query, typically it's a search is done, and based on those search information you get on like side panes, recommendations pop up on what you may like, or customers who bought this also like this, stuff like that. Because of LLMs, they've been trying to shift a bit more to a conversational flow, primarily to account for what we call in recommend or in search spaces as broad queries, in the sense that in search there is this idea of broad queries and narrow queries. If you search for something like great value pasta, that's a fairly narrow query because you have a brand and you have an item that you're specifically searching for. Broad queries are like, I'm planning a dinner for 12. Could you give me a menu that's sort of Italian themed that I can serve to these people along with recipes? So that's more of a broad query where there isn't exactly an item, but there's more of an underlying need, and you want to cater to that need. So LLMs have been used in like search and recommendations to sort of facilitate broad queries and to facilitate a more conversation flow. So that's primarily where LLMs have been used thus far. So hopefully that gives you a mental map of A, the recommender system space, content-based, collaborative, hybrid, sequential, these four buckets, a few models under that buckets, and B, the LLM space and how LLMs have been used in RecSys thus far. There have been like a few models that have tried to do what the current authors are doing of integrating LLMs and RecSys deeply. But this one has sort of gotten results pretty significantly higher than what SOTA results are. So thought I'd start out with this paper. Cool. Now coming to the architecture. So what the authors propose in terms of a model is how they integrate LLMs and recommender systems is by creating two language models. The first one being an item language model, and the second one being a user language model. So again, to clarify, the task that they're focusing on is the sequential recommendation task. Essentially, given items I1 to IN for user U, given that we know that user item interaction history, what is the next item that the user is gonna interact with? So to solve for this, the architecture that they propose is using language models to create sort of two separate item language model, item large language model, and user large language model. So the item large language model essentially, like as commonly done in the field, takes like the title, the text, all of those descriptions to create like an item embedding that's very informative. And since it's a large language model, the world knowledge, the authors propose that the world knowledge will come into play here and create a bit more informed or nuanced embedding than typical language models. And this item language model is then fed into the user language model. The user language model what it does is it takes in each of the previous items that the user has interacted with. And these items are again the embeddings of the items that we got from the item language model. So each of them are embeddings. And they're not just the item IDs, which are typically done in other models like SASRec or even BERT for Rec. They're based more on ID of the item. Here, it's the actual embedding from text and title that we are able to decode. So all the item embeddings are taken in sequence, and this new item embedding is sort of passed, and we try to predict if the user will actually interact with the item or not. How exactly this item embedding is passed into the user LM, we'll come to that in like a few slides. But the main takeaways is sort of like the item language model to get the item embeddings, and the user language model, which takes the item interaction history and predicts whether a user will actually like an item or not. And what large language models are they using? They're using Tiny Llama. Tiny Llama has like 1 billion parameters, and it's a I mean, if you have certain compute, if you have certain restrictions, then 1 billion parameter model is like a Tiny Llama 1 billion parameter model is like a pretty decent go-to. The other language model they used is 𝗬𝗁𝗂, which is again like new to me as well. I haven't actually come across it. It's an interesting choice. They haven't actually discussed why they use this particular model, but let's assuming that this model is sort of like a run of the mill in the sense that it's one of the top 10 performing models. The results, what they give, should sort of be fairly valid, I would say. So Tiny Llama and 𝗬𝗁𝗖 is sort of like the two models that they've been using in these large language models to create these item and user large language models. Now, coming to the next one, the approach, how do they actually go about training these two models? So they actually train for two tasks, generative and discriminative tasks. The generative task that they train for does make sense because typically sequential recommendation systems are trained on the generative task of predicting what the next item that the user will like is. So you feed in for a particular user the entire item interaction history. It may be like 50 items long, 100 items long, whatever. You feed that into the model, and the model gives you a prediction of what the next item is going to be. So that's generative task, and that's typically what's done in sequential recommendation systems. The two models that they're comparing it to, SAS for Rec and HSTU, we'll come to them in a bit. But those two models sort of work in like a generative manner. They're trained in generative manner, so the generative task makes sense. And the loss function that they're using is info and NCE loss. It's essentially a loss function that tries to, so how the training proceeds is they take, for a particular user, they take the user's entire, let's say a 50 length interaction history, and the label is sort of the next item the user will like. The positive sample, like essentially. Now they don't have negative samples, so what they do to create negative samples is from the catalog they pick randomly maybe 10 or 20 items and they assign them as negative samples. The only condition is these 10 or 20 items shouldn't be in this user's current user interaction history. So they are considered the negative samples. And what the info-NC loss does is to maximize the similarity between the output of this model and the positive item, and minimize the similarity between the output of this model and all the negative items. So that's what info-NC loss tries to do. It tries to do that kind of balancing act, and it's a fairly standard loss function, I would say. Um, they also train it on a discriminated task, which kind of, I mean, at least from the paper, I wasn't able to fully understand why the discriminated task comes into play, in the sense that given a user an item, they want to try and figure out if the user will actually be interested in that item or not, essentially a 1 or 0 prediction. And in 1 or 0 predictions, you can use a typical loss function like a logistic loss function. Um, so uh, why they're doing that discriminated task is because they want to run, they want to show its performance in an online testing scenario or an A/B testing scenario, and show that this model actually is able to perform better than baselines. Um, so that's why they're doing the discriminated task. But why they didn't use the generative model, the fine-tuned model, and just add a layer on top of it, or sort of use the same approach that SAS4Rec is using and restrict it on just the offline evaluation. Not clearly specified in the paper, but definitely if they want to do an online A/B testing, discriminative is sort of the way to go, and in that sense, it does make sense. The design choice isn't fully explained, but definitely like an interesting approach of doing both, which is kind of new, which is kind of new to me, at least, I would say. And in terms of how they're actually doing the training, or how they're, like I mentioned, they have two LLMs, the item LLM and the user LLM. So how are they actually using it to calculate the loss function and improve these LLMs? So like I mentioned, the item LLM provides all these embeddings, and you feed the embedding to the user LLM. Um, you feed these embeddings to the user LLM, the E1 to EN being the user interaction history items, and the E target being the new item. So this is called early fusion, where you involve the target with the interaction history, and you try to figure out if this target would have been a 1 or a 0. So both of these are for discriminative tasks. So you try to figure out whether this target would have led to a 1, as in the user will interact with that item, or a 0, the user won't interact with that item. Early fusion is good because it gives you really good results in terms of performance, but it's not actually practically possible to sort of um, put the target in before the user LLM, because it means sort of like um, it essentially means that whenever you want to make a prediction between a user and item, you need to create or train the model for all the possible user item combinations. Whereas in this one, once the model is sort of trained, you just need to pass the embedding to just the prediction head. So that makes it a lot faster. But late fusion being where you feed the target only to the final prediction head, does have certain performance issues, but it's definitely a lot more faster, lot less compute intensive, and a lot more seen in actual practical scenarios. So this is how the discriminative task is sort of trained for, and the generative task is pretty similar in the sense that you feed the embeddings to the user LLM. This target is in there, the prediction head, logic, none of this is there. The embeddings are fed into the user LLM, and it tries to predict the embedding for the next item. And the info-NC loss sort of works on that embedding that's outputted from the user LLM. So yeah, this is sort of how training is set up. There are a few more parameters which seem to be like standard parameters in the paper, in the sense that they use, I think, in item embeddings, for creating item embeddings, the text size is limited to like 512, a learning rate of 1e minus 4. They didn't use an adaptive learning rate scheduler, I think, which is kind of interesting, because most LLM research does show that adaptive learning rates schedulers and warming up the parameters before fine tuning, all of this does help. So they haven't done, or at least I didn't see it in the paper. which is kind of interesting. Maybe they've done it. But yeah, they've used certain parameters, and all those parameters seem fairly standard to me. If you guys have like anything that you want to call out that's interesting in the paper, feel free to drop it on chat. So yeah, that's pretty much how training is done. Coming to the next section, which is like the setup. So how we have already covered like the model, how the model is sort of trained using the labels, trained using the interaction history and sort of labels that are generated. Now, how exactly are they sort of evaluating everything? So the data sets that they've selected is PixelRec and Amazon Book Reviews. Amazon Book Reviews is like a pretty common one, a lot of textual data, and it's pretty standard. PixelRec is typically used for like multimodal recommendation systems because it has like images. So it's an interesting choice, but it does have like title and text, so it can be used for like these kind of models. I mean, it's built for multimodal, but it can be used for text alone as well. In terms of benchmarks that they want to compare this HLLM to, they've used SASREC and HSTU. SASREC is a pretty dominant one in sequential recommendation tasks in the sense that, like I mentioned, SASREC is nothing but whatever your user interaction history was, it creates an embedding out of that. It could be a multimodal embedding, it could be just a text alone embedding, and then it applies an attention mechanism on it to figure out uh, within your user interaction history what was important for the next item, what isn't important for the next item. It's a pretty I would say dominant or like a pretty good SOTA in sequential recommendation systems. HSTU is an interesting choice. It's a different way of doing sequential recommendations. I don't know if it's considered SOTA. So HSTU, it's similar to this in the sense that it also works on user interaction history. It also uses embeddings. But if let's say you have a user interaction history of 50 items, that's what you call your main time span of a user, like the 50 item user interaction history. So what HSTU does is it creates auxiliary interaction histories from this one. Like from this 50, it maybe takes this 10 or this 10 or this 10. And what it tries to um, essentially what it tries to do intuitively by that is to capture like short-term and long-term trends. From the main one, it tries to capture long-term, and from these auxiliaries, it tries to capture short-term trends. It's an interesting approach, and it imposes like a hierarchy on top of them, sort of like giving more emphasis to some of the short. I mean, like you can adaptively emphasize the short-term or long-term. It's an interesting approach. Don't know if it's like SOTA, but it definitely does help compare this approach to another flavor of approaches in sequential recommendation systems. Coming to the metrics, they are using recall at K and NDCG at K. These are like standard metrics in recommendation systems. If folks are fairly new to this, like I mentioned, once the session is over, I'll be uploading this on YouTube, and I'll be linking most of my notes that I sort of develop along with every session in that. So the notes will cover the links to all these resources that I'm showing. I just wanted to quickly show it so that folks understand the metrics, because you need to understand the metrics to understand the results. So in case anybody doesn't understand the metrics, I'll just quickly go over them. So in recommender systems, we typically use this at K metrics primarily because it doesn't matter if you're, let's say you provide a recommendation of 100 items. It doesn't matter if you're accurate about the bottom 10 of those 100 items. The user will only probably see maybe the top 10 or top 20. So that's why we use these at K matrices, where we evaluate only on the top K predictions that the model has made. So recall at K, essentially, it works very similar to recall. The only difference being that it only takes the top 10 predictions that the user has made and tries to see how many of them are actually relevant. Um, so how many are relevant in this top K, and how many actually relevant items did the user actually interact with? So let's say the user had 8 items that they actually interacted with. We were able to predict 5. The recall will be 0.625. Now, the problem with recall at K is that where these relevant items occur in the list doesn't matter, in the sense that if the relevant item were in position 1 or if the relevant item were in position 6, it doesn't matter because it doesn't take the ranking into consideration. But from a user experience, if relevant items are closer towards the top, it's a better user experience. So to take that into account, there is another metric that they're choosing. There are multiple metrics you can actually choose, but the one they're using is NDCG at A. Basically, what it does is it's important that the ranking of the or the position of where the accurate prediction is in that top K does matter. So if the position is higher, or if the position is essentially rank 1, rank 2, therefore the rank is lower, then NDCG would be higher. And you want NDCG to be higher, you want recall to be higher. So just a quick overview of like the metrics. And in terms of how they're evaluating the approach, like I mentioned, they have two different evaluation mechanisms. For offline testing against recall and NDCG, they are using a generator task. They're fine-tuning on the generator task. This is what the generator task is also what SAS and HSTU are sort of trained for. So that makes a lot of sense. For the online A/B testing one, they're using the discriminator task and they're training the model on the discriminator task. The paper is kind of weirdly doesn't provide a lot of details about the online task, including like a table comparing its results with the other models. So that's kind of a maybe something the paper could have improved sort of thing. But yeah, they're using it for the discriminator task, and definitely like would love to see more research around how these kind of LLM plus recommender systems models works in actual A/B testing. But yeah, this is the current setup that they have, current evaluation mechanisms that they have. And in terms of results, quickly going over them, what they're essentially saying is the pre-trained weights do make a difference in the sense that LLMs do encapsulate world knowledge, and that world knowledge does make a difference to recommendations that are made. How they're doing it is by using the models, the tiny LLM or the 𝗬𝗁𝗼 models with like weights that are randomly initialized versus weights that are pre-trained, and we can clearly see if you use the pre-trained weights, the performance is actually much better. And they're also showing that the number of tokens the LLMs uses actually does matter. So as you might know, like LLMs are built upon like text that's grabbed from multiple sources, and they essentially end up creating a huge vocabulary. The number of tokens, the number of words or subwords based upon how the LLM processes things is essentially what's called a token. So as the token size increases, the performance typically also increases in the LLM space, and we see that in recommender systems as well. As you increase the token size, the recommendation systems performance also increases. The next question that we had was fine tuning. Is that actually necessary in the recommendation system space? Essentially, can we just put in those tiny LLM, tiny llama or 𝗬𝗁𝗼 models, freeze the weights, and just work on the in this case like the prediction head, or once the embeddings are produced, the user LLM interacts with this, and can we just work on this? Can we just find or adjust the weights for this prediction head and keep everything else frozen? And from their results, they're showing that keeping the parameters learnable is actually better, and you get better performance from that. So fine-tuning LLMs in the recommender system space does add value. And the last one, does the performance improve with scale? Like typically we've seen in the LLM space, as the number of the size of the number of parameters or the size of the LLM increases, the performance also increases, like on the massive multi-language understanding, which is like the SOTA benchmark data set for question answering. As the LLM parameters increases, they've been able to do better on those data sets. So does that translate into recommender systems? Yes, it does. They tried out with like the 1 billion and 7 billion models, and they've shown that as the size of the LLM increases, the performance also does increase. So scale does help LLMs, which does kind of make sense. Like if as the size of LLMs increase, they're actually able to capture world knowledge better. Then yes, it does make sense that as size increases, it could help in LLMs as well. Now, the most important or sort of the most important question, one, does LLMs outperform the SOTA sequential recommendations, which is like the SAS and the one that they chose is HSTU. So yes, they do show that it does outperform, and by an improvement of like 22%, which is pretty good. I would say like pretty significant results. And especially as they increase the model size, they're saying that model size being the parameter size that we just discussed before, they see even more improvement. So this is like pretty interesting and slash exciting results. Now the other question is, yes, LLMs do add value. That makes sense, and this kind of improvement is quite significant. But can we actually use it in production settings? So what they're saying is, the LLM model is actually more data efficient in the sense that if you have a limited amount of not exactly a limited amount of data, but data in like production grade systems, which um, once you hit that production grade, if you have limited amount of data, LLMs are actually able to get more out of that data than traditional ID based models. So they're saying that it is more data efficient, and they do show results for that, which is kind of interesting. And they're saying that if those models, these models, the LLM-based models, can be made efficient enough for these kind of large-scale online recommendation systems. And how they're doing that is by having this sort of interesting flow, where they create the item embeddings when the item is created. So item embeddings just takes item description and title. So as soon as the item is created, you can create those embeddings and you can store it. You don't need to necessarily update those unless you retrain your item LLM, maybe like once in a day, once in a week, something like that. So you don't need to necessarily update that LLM very often. Next one is the user LLM, and what they're saying is you take the user interaction history for uh, at the start of every day, and you pass it through the user LLM to create the set of items that the user could interact with, or you create the user user item embedding, and you store both of these into something like a DB or something like a vector DB. And during the online recommendation, the only thing you want to do is you want to fetch the item, fetch the user, and try and make a recommendation of what the user will actually like. It's an interesting system. They haven't done a lot of work around like throughput or latency or staleness, in the sense that typically such systems that run once in the morning towards the maybe midday afternoon, their performance might not actually keep up, especially with users who interact with website very often and whose interaction history might change. So those kind of metrics like throughput, latency, staleness, those things haven't been addressed in the paper, and it would be really cool to see like future works address those things. But it's definitely like a somewhat standard and somewhat interesting approach towards using these kind of systems in a production setting. Now, so we covered basically what the paper wanted to address, the research space, the approach, how they trained the model, how they evaluated the model, and the kind of results that they obtained. Now we sort of switch over to what we liked about the paper or what we didn't like about the paper. In terms of what I personally liked about the paper, um, um, the approach of using item embeddings with LLMs to create, sorry, having an item LLM to create an item embedding, that sort of does seem common sense at this point, and them using that is pretty good. The other one, the user LLM, where they convert item embedding, sorry, items to item embeddings and pass that as sort of input to the user LLM and create the next item embedding. That kind of generated task, I feel like is a very interesting or somewhat new approach. Makes a lot of sense. simple, but at the same time quite new as well, which are sort of like the approach that I often like and I feel are often effective. Now, in terms of what I maybe felt a bit off or a bit odd, all the dataset metrics and benchmarks are standard. HSTU seems a bit odd because at least based on my knowledge, it may not be considered like SOTA necessarily. And generative and discriminative task, the training for both of them, like one for comparing against the benchmarks, one for comparing against online testing, that I understand. But in the online testing, they don't give a lot of results, I feel. And they could have done a bit better to help understand how it's actually performing in an online setting, like especially like I mentioned, latency, throughput, staleness, stuff like that. So that I feel like they could have done a bit better. And yeah, definitely in terms of like what I feel like or what I am looking forward to is seeing more of these LLM recommender systems in production and trying and sort of seeing how well they actually perform, especially from a scale perspective. Because yeah, recommendation systems, getting recommendation systems to perform at scale it's a very complex engineering slash machine learning task, and I'm very curious to see how these systems would actually stack up. Yeah, and yeah, sort of this is a section like if we have any questions on chat, we'll take them. Just a quick sort of reminder, we'll have like another paper on next Sunday. It's probably going to be a RecSys related paper, more of a pure RecSys related paper. I'll be announcing that paper in the coming next 2 weeks or not, or so. Sorry, next 2 days or so. Monthly project builds we're going to start in November, and study groups we're going to be launching in sorry, monthly project builds we're starting in October, and study groups in November. Do make sure to follow us on all our LinkedIn handles, Instagram handles, and YouTube handles. Instagram and YouTube are sort of still being built up, but do make sure to follow us for all the updates. And yeah, let me see if there are any questions. Hey, Aditya, hey, Ritik. World knowledge equal to data. Is this correct? Yeah. So how LLMs are trained, like if you look at Llama, which is sort of the most open one in terms of how it's built, they take a lot of like Wikipedia data set, they take a lot of textbooks, they take all this information and they build the LLM on top of it to try and condense all the information in all of these textual components, recently even image components um, into sort of like dense embeddings, which is what we call, and what researchers hypothesize is that those dense embeddings have world knowledge encoded in them, at least from the perspective of like next word prediction, like what should come next. From that perspective, at least the models have some kind of world knowledge embedded in them. Can you provide the link to the paper? Yeah, it should be there in the so when you registered, it should have been there. But let me just quickly drop the link as well. My bad. Didn't see this earlier. How will you rank a prediction? If it's a discriminative task, you will have a probability of whether the user likes a particular item or not. So higher the probability, higher the rank of the prediction. And if it's like a generated task, you're essentially generating what the next item that the user will like is. So there's no ranking there. You use info and C loss there, and whatever the item that's predicted, you try and sort of whatever items are predicted, maybe you run the model like 10 times. Those 10 items that are predicted, you use them in sort of like the ranking. I mean, in the order that they're in the order that they're predicted, you use them in that order for ranking. Probabilities in Rajat didn't quite understand what that meant. Probabilities as in a recommendation system like this is gathering the data real time, which adds to world knowledge. Does that affect its performance? It isn't necessarily gathering information in real time, like especially in the inference setting that I mentioned. Item LLM is only the item embeddings are created only when the item is created, because again, it's the assumption that the researchers are making is that the item description, once they create, it never changes. It's not actually true in real world settings, but let's assume for academic settings it's true. Item description, item title change stays the same. So when the item is created, they create the item embedding. So it needs to be run only once, and it's stored into the vector DB. User LLMs, it's run once a day. So again, it's not maybe learning the real time, which is maybe a kind of drawback of the model. But yeah, typically, like in recommendation systems, also you don't have the base model doesn't really learn real time. You have a candidate generation model, you have a ranking model, then you have a re-ranking model. So the candidate generation model, which could be like this model, it typically learns maybe once a day. Like it's done. I would like, at least the papers I read from YouTube, TikTok, Alibaba, they usually run these candidate generation models like once every 24 hours. And then the ranking and re-ranking models are what sort of updated more frequently, once an hour, or once every 15 minutes, once every 10 seconds, stuff like that. So this could be just a candidate generation model. It doesn't really need to, it doesn't need to learn real time. So it's purely experimental at the moment. Yeah. I haven't like, this is a paper from ByteDance, so essentially a company that parent company of TikTok. So yeah, when they come out with recommended systems paper, I always kind of pay attention, primarily because like they captured like short-term interest recommendations fairly well, and especially like solved like cold start problems, I think, fairly well. So yeah, when they come out with RecSys papers, I feel like, oh, they might be actually doing some of this, at least in some of their models.
So they're not gathering this real time. It's already set for them for this experiment, is what you're saying?
Yeah, the data sets is like PixelRec and Amazon book reviews. So those two data sets, they're the offline evaluation that they've shown for those, that is in real time. The online evaluation, the A/B testing that they've shown, the problem is the paper doesn't really describe it that well. So I'm guessing it's maybe something confidential to the company, but the only thing that they mentioned is that they've done the A/B test and they've seen this kind of improvement or performance improvement. They haven't compared it that well with the other systems. They haven't shown latency, throughput, staleness, any of those results. So I'm guessing like it's something. It's a bit hard to, especially like when companies sort of release papers, sort of you might have to do a bit reading between the lines, in the sense that, okay, maybe they're actually using this. Maybe that's why they're not releasing some of the information. But yeah, at least in this paper, they've shown that it does improve in an A/B test that they conducted. So could they be using it in their systems? Maybe. Can we have a Discord server? Yeah, BuildML does have a Discord server. We're going to be again launching in October. Primarily, it's just me and a few other guys from India, so it's taking a bit of time to set everything up. Yeah. Please explain the metrics used in the paper. So yeah, the notes I'll be sharing later, and this is a really good link. Evidently.ai is a really good site to understand all the metrics that's used in the paper. AI Summer is a really good website to understand the recommender system space, and all of these links again will be in the notes that I link along with the video when I upload to YouTube. So everyone will get it, and hopefully the notes have a bit more detail in the sense that like more than I can cover in an hour. So it covers like the SaaS rec and HSTO architectures, and where you can go and read a bit more about them, and a few other things that hopefully you'll find useful.
This is my first exposure to like recommendation systems, so it's been
awesome.
a while, but it's nice.
Awesome. Yeah, thank you. What do you believe will be the main applications of this rec system? I see it as helping for tasks that can help the person connect to something they wouldn't have thought of before, but it's highly relevant to their task. Yeah, I think incorporating world knowledge definitely does help, because the idea of like using knowledge repositories has been like fairly common in recommender systems. So I feel like LLMs is like have sort of, I wouldn't say solved that problem, but made a lot more progress than maybe what has been made till date. So I feel like that world knowledge component is going to be very valuable, and it's going to is probably already integrated with a lot of RecSys that we have nowadays. And I think that integration is going to get more and more deeper, and we're going to see more and more techniques. And I feel like if you're working in RecSys, um, taking a look at LLMs, trying to see how you can leverage that world knowledge and these interesting ways of converting the user interaction history and feeding that itself into an LLM to see what it can come up with. Um, those kind of things are definitely interesting. Those kind of experiments, I feel like, would become more commonplace in the RecSys space as well. And in terms of like how it can help, especially I feel like it's going to be effective with cold start. I feel like if they had done an evaluation specifically for cold start items, they would have seen like a lot better uh, performance improvements. Primarily because the user interaction history is going to be absent for cold start items or cold start users. But these kind of world knowledge models have a have this capability of starting from a better place than typical cold start models would be able to start from. So if they're focusing on those kind of things, I feel like that kind of results would also be pretty useful. So cold start is something I'm definitely going to be looking out for those kind of papers more, LLMs and how they address the cold start problem. Uh, how does this fare against GNNs for SQL recognition? Anywhere these better than GNNs in metrics or online service? Yeah, so GNNs is another metric that I would have seen. I would have liked them to compare it against some kind of GNN like GraphSage or something of that sort. Um, Primarily because in sequential recommendations, yes, SAS for rec is a pretty dominant benchmark, but it's more attention based. If they had used like a graph neural network instead of HSTU, I feel like the results would hold a bit more strength. But SAS for rec is a pretty dominant benchmark in that space. So getting performances above SAS for rec is significant, I would say. But yeah, GNN is something definitely that the paper could incorporate. That's a good call out, Ritik. How good are these? Yeah, cold start problems. Awesome, awesome call out. Yeah, I think yeah, in cold start problems, this would be um, really good in cold start. Thanks, Rajat. Thanks for answering. Could you explain more about how this could be used, how this could be tested for latency? So latency primarily is going to be like when they run this model at inference time, primarily because in recommendation systems to account for latency, like in actual production grade recommendation systems, they don't actually work one-on-one. They do batch recommendations. So they get a bunch of interaction history or clicks and streams, and they absorb that into the re-ranker and they provide recommendations. So they're going to be providing batched recommendations. So do they want this to be an actual foundational candidate generation model, or do they actually plan on using this for like a re-rankers or rankers? Like Two Towers can be somewhat used for, I would say, ranking, maybe not re-rankers, but it can be used for ranking. This one, do I think it can be used for ranking? Primarily because they're freezing everything and sort of storing everything. Maybe not. I think they're assuming that we'll be using it for candidate generation. In which case, fairly good. Would still like to see how if staleness actually affects this or not. But yeah, latency test would primarily be how much time it takes for them it to respond, how to make that recommendation, and how it does with like batching recommendations together. Uh, awesome. I think that's all the questions, and I think we are at
I did have
time.
one.
Sure, sure.
Yeah, sorry. I didn't write it in the comments. Thinking about the space in general, and one subject that's always kind of concern is explainability, like
Yeah.
versus the complexity. Like, how do you see that in the whole space in general? Like, where does a simpler model like content-based filtering is probably better to use than a LLM-based approach, or how do they deal in general with that kind of problem?
Yeah, that's a really good question, especially explainability and bias in recommender systems. I feel like a lot of research papers don't address it. Like, so bias is like in recommender system, the most common bias is the popularity bias, where you typically tend to recommend the popular movies. Like if let's say a person doesn't like Marvel movies in Netflix, if a Marvel movie is going to be launched, it's going to be recommended to you, even if you don't like maybe those kind of movies. So that's like a common bias in recommender systems. There's a lot more other biases, but bias is like often lacking in these papers, and they don't do that kind of study. So I feel like a good data set for detecting and evaluating bias is something that could come up in this space. And like you mentioned, explainability. generally in this DL space, not just in RecSys, I feel generally across in DL, explainability has been sort of lagging behind. Most people just hope tap helps, but in these kind of large models, it doesn't make a lot of sense. There have been people who have been trying to take out slices of the like layer wise. They try to take out the values and try and connect to examples. Okay, when this example happens, these neurons are triggered. When this example happens, these neurons are triggered. So can they make interpretations out of this? It was done in the attention paper initially, attention, that's all you need. That paper actually did it, but from then onwards I don't see it like being rigorously done in all papers. So explainability and bias, both of these very good questions. I would say I don't have an answer. I feel like there aren't really good data sets that help researchers do that. So maybe starting out with solid data sets for that, and then maybe researchers might pick up. But yeah, explainability, for now, it seems like as long as things go good, people are okay with accepting like these kind of black boxes. Yeah. Is that because the number of similar embeddings to a Marvel movie would be a lot when it's launched? I didn't understand how bias would be produced. So yeah, the idea is so popularity bias is primarily because a lot of people are interacting with that item, and among those people, it's likely that a person similar to you, as in a person who like the same items that you like, that person is more probable to be present. The Marvel movie would be recommended to you. So it's this idea that since popular items are items that are liked by a lot of people, it's more probable that a user who's similar to you will like that item, and therefore it will be recommended to you. That's the intuition in the collaborative filtering space, and it's fairly clear in the collaborative filtering space. So popularity bias is sort of somewhat common in recommender. I would say pretty common in recommender systems. But yeah, hopefully that answers the question. Let me know if it doesn't. Awesome. Cool. So yeah, I'll stop the recording, and the recording will be up on YouTube in like 2 or 3 days, along